our today's video or lesson, and this is part 2 of the nuclear processes. I hope you've now watched part 1, and now this is part 2, and your teacher still remains teacher Aheba William. And please support us by subscribing to our channel, sharing with friends, liking the videos we put there, so that we can be energized to continue sharing this content. You can as well reach us out on either WhatsApp, which is 751 40 71 58. We shall be able to respond to all your queries. Even if it is appreciation, we welcome it. Now let's continue from part 1 of the previous video, which was nuclear processes part 1. We looked at half-life. We ended by looking at half-life. We had seen what half-life means, the time it takes for a substance to decay to half of its original mass or to half of its original count rate or activity. That's what we call half-life. And we had ended by looking at this example where we had seen that during a mining activity in Mubende, a rare mineral was discovered, but the miners were warned that the mineral was radioactive and hence could cause health problems to them if they continued exposed to it. When scientists conducted a study on the mineral, the following results were obtained, and the results were as follows, whereby when the time was 0 minutes, the count rate was 800, and when the time was 4 minutes, the count rate was 520, 8 minutes 345, 12 minutes 225, 18 minutes 145. And then the task was that, as a scientist, determine the half-life for the substance, and you as well determine after how long will the radiation be at a safe level. Remember, they said that if it is considered to be at 200 counts per second, if when the count reaches 200, then the radiation is said to be safe. Then after how long will it be so? So we had seen that for us to address this question, we can take up since we don't know the half-life, we can use the graphical approach. Like how we plot the count rate against time, then we see how the graph comes out looking like. So we looked at our graph, and we said we can first have our values here so that we plot them. If you draw your graph very well, you see that your graph will come out like this, because if I draw my vertical axis, horizontal axis, I put my values vertically. Since the highest is 800, the smallest is 145, I can start from 0. I use a scale of 100, 100, 100, which is 100, 200, 3, 4, 5, 6, up to 800. Then horizontally, I can use a scale of 2, 2. Since the smallest is 0, biggest is 18, I can use 2, 2. I start from 0, 2 minutes, 4 minutes, 6, 8, 10, 12, 14, 16, 18, and so on. When I plot, when it was 800 counts, 800, the time was 0, so meaning I plot here. When it is 520, 520, that is around the second, because vertically each small division is 10, 10, 10. So 520, meaning those will be 2 divisions after 500. So that means I put there in the second division, 520. The time was 4. When it is 345, 345, meaning I'm going beyond the 4th division, the time was 8. I plot there. When it was 225, the time was 12. So I plot there. Remember, I'm picking my values from here. When it is 148, the time is 18. I come and say 148 is around the 4th division or closing to the 5th division. So 145, when the time is 18, I plot. So I have my 4 plots, the 145, the 225, the 345, the 520, the 800. When I join them with a smooth line, it will form this curve that we can see here. So after getting my curve, now I have, this is what we call the radioactive decay curve. Now I can determine half-life from it. How? Remember we said you look, the original mass was 800, meaning I need to know how long did it take for it to decay to half of 800, which is 400. To decay from 800 to 400, what was the time? I'll come at that half mass, which is 400. I extrapolate, I reach the curve, and I see what is the time that corresponds to 400. From the curve, I see down here, it is around the second division, and each division here down is 0.2. So meaning if there are 2, that is 0.4, meaning I add it on a 6, it will be 6.4. So I see that the half-life from the graph, it is 6.4 minutes. The other question was that after how long will the radiation be said to be safe if the safety level is 200 counts. So we need to come and see at 200 what is the time. At 200 we see that the time is when we read here, it is the fifth division from 12. Now if each one is 0.2, meaning from here it is 12.0, the first one will be 12.2, the second one 12.4, the third one 12.6, the fourth one 12.8, and the fifth one will be 13. So it means that at 200 counts per minute, the time will be 13 after 13 minutes. Therefore, the miners should always wait after 13 minutes every time they come across that mineral. That's how this is a recap from where we had ended part 1, and as your class or as a group of colleagues, you can have this group discussion with you. You write it down, you'll discuss it at your free time. And the question goes as follows: a certain lotion has created skin problems to people, and the government is considering banning the company since the lotion is said to contain some radioactive substance. Scientists conducted a study on the lotion by exposing it to sunlight, and it generated the following results. So scientists are trying to study what is the issue with this lotion. And these were the results: that when time was 0, the number of particles present were 800. At 10 hours, after 10 hours, it is 560. After 20 hours, 400. After 30, 280, 40, 250, 160. 60 hours, 100 particles. 70 hours, 40 particles. The task now is determine the half-life of the radioactive substance in the lotion and estimate the count rate after 64 hours of exposure to sunlight. So they want you to do two things. One, determine what is the half-life of the substance which is in this lotion. Secondly, what will be the count rate after 64 hours of exposure to sunlight? Okay, meaning you need to know that. I believe you'll be able to do it, and that is for you to discuss with your colleagues. Let's now look at the next part, which is nuclear reactions. Now, nuclear reactions, here we are looking at the reactions between the nucleus. Like you hear the word nuclear reaction, reactions happening in the nucleus. We had seen earlier that the nucleus can disintegrate, which we called radioactivity, but the nucleus can as well react in two ways: by fusing or by fission. Fission, then fusing. Now, when we say fusion and fission, I know very many people have challenges when it comes to mentioning those two. Now, let's look at what they are. Nuclear fusion, Fu, that is fusion. Then Fi, fission. What do they mean? Fusing, like you hear the word fusing, it is basically coming together. So under nuclear fusion, this is where you have two light nuclei that come together at high temperatures. If you look, there are key terms here. One is union or combining of two light nuclei at high temperatures to form a heavy nucleus. But as they are joining, they release a lot of energy. Okay, so those are three key things you need to look out for. One, combining. What are combining? Two light nuclei. When they combine, what will they form? They will form a heavy nucleus. When they are forming a heavy nucleus, what happens? There is a release of energy. That is what we call fusion, fusing, Fu. That is joining, two things are joining together. Like you can look at it in form of, let's say, when you have bricks, you're joining bricks, you can end up producing a big structure, which is a house. That is meaning you're fusing particles or you're fusing nuclei. Whereas fission, Fi, this is the splitting of a heavy nucleus and a stable nucleus. Remember when you're looking at the topic of atomic structure, you saw that if a nucleus is very heavy, the chances of it being unstable are high. If it has more neutrons, then it will start becoming unstable. So if it becomes very, very unstable, it will end up breaking up. Now that breakup is what we call Fi, fission, or others call it fission. So that is the splitting of a heavy unstable nucleus, and when it splits, what happens? It will break to form two lighter nuclei with the release of energy. I hope you get the difference. Fusion, two small ones combine to form a big one at high temperature to release energy. Whereas Fi is the one big one break up to produce two smaller ones by releasing also energy. Now, when does these two happen? Or what are the conditions for these two to happen? Some of the conditions you already see them, that for fusion to occur, then you must have two smaller nuclei. For Fi to occur, fission, then you must have one heavy nuclei that will break. Now, when do they happen, or what are the conditions that can enable them to successfully happen? Because sometimes you may have the two and they refuse to come together. Now, these are the conditions. Condition number one, for two lighter nuclei to come together, there must be a very high temperature. For what? The high temperature enables these particles to overcome the nuclear reaction. Similarly, these two nuclei, these two smaller things, must be moving with a very high speed. They must be moving at a high speed so that they are able to overcome the nuclear repulsion. Remember, these are nucleus. The one is positively charged, another one is also positively charged, because we know the nucleus is positively charged. So if they are coming together, then they will be repelling each other by the law of electrostatics. So to overcome that, they have to be moving very fast so that they cannot repel each other. By the time they get to repel, they will have collided into each other and they will have joined to form one. Whereas for fission to occur, condition number one is there must be low temperature. For a heavy atom, for a heavy nucleus to break, it needs lower temperature. It doesn't need a high temperature. Secondly, you must have a fast moving neutron. Now, what is the role of a fast moving electron? A fast moving neutron. Its role is to destabilize more. Remember, this thing will already be heavy. It's like if I tell you you're carrying something that is very heavy on your head, and then you're standing there, you're almost falling, you're already unstable. What will happen if someone comes and pushes you slightly? You'll tell me that automatically what you are carrying will easily fall down, or you'll let it go, it will fall down. Exactly, that is the role of the neutron. The neutron comes in, and when it strikes this heavy nucleus, it makes it to become more unstable. It was already heavy. It's like you're carrying a sack of, let's say, you're carrying a sack which is containing, let's say, bricks. You already loaded, then another person comes and adds you another brick which is beyond what you can carry. Automatically you lose everything. That's what exactly happens here. When we look at it, these reactions in form of equations, we can look at fusion. We may have two nucleus, one of a hydrogen atom which is having one neutron and one proton, joining with another hydrogen atom. When they join, what will they form? They'll form what we call the deuterium, or what we call hydrogen 3, okay, in simple terms. It can be hydrogen 3 or helium 3, or they can even form a helium atom. And when they join, if they form this hydrogen 3, remember we said total mass number on the left should be equal to total mass number on the right of the equation after the arrow. Total mass number before the arrow should be equal to total mass number after the arrow. So when they join, we see that the hydrogen formed is having a mass number of 3. Yet this side the total mass number is what? Is 4. Because you're having 2 plus 2, which is 4. So it means there is one mass number that is missing, one particle that is missing. And remember what forms the mass number? That is protons and neutrons. So one neutron will be released. You see that? So that is the neutron released. So, and when you combine them, you realize you have now a total mass number of 4. Mass number of 4. Atomic number here, it was 2. And the atomic number here is also, oh sorry, it was supposed to be 2 here. Sorry. So we are saying that if you look, 2 hydrogen atoms, they can come together, they fuse to form a helium atom, which is helium with a mass number of 3 and atomic number of 2. And when this forms, it releases an electron which will be produced, and as well as a lot of energy that will be produced. So that is for fusion. You see that if 2 nuclei come together, they can produce a new nucleus, plus accompanied by a neutron, and then some energy released. Now the number of neutrons produced depends on the nature of the nucleus formed, because sometimes you may find if they joined together to form, let's say, a helium atom which is of mass number 4, then there would be no neutron produced. Okay, if they joined together to form a helium atom with now mass number 3, meaning there will be a neutron produced. Why? Because the total mass number of the products must balance with the total mass number of the inputs, and the total atomic number as well must be balancing. So there is a lot of energy that is always produced. On the other hand, when we look at nuclear fission, which is the separation of a heavy nucleus, we can have a nucleus which is like uranium-235. This is a very heavy, you can see this is a very heavy nucleus with a mass number of 92. Remember we said for fusion to occur, you must have a fast moving neutron. So when a neutron comes and hits this nucleus of uranium-235, the uranium-235 will separate, forming 2 nuclei. One nuclei will be having 56 protons, and you can tell now how many neutrons. So it will be having a mass number of 144, and another nucleus will be having a mass number of 89 particles, meaning 36 of them will be protons. So we know a nucleus which has that mass number will be barium, and the nucleus which has this mass number of 89 will be krypton. So uranium-235, when you hit it with a neutron, it can break into 2, forming barium-144 and krypton-89. Remember, all these are isotopes. This can be an isotope of barium. It can have a different nucleus of maybe 141. Same applies to krypton. It can be of 90, 91, 92. Those are isotopes. You looked at isotopes under the topic of atomic structures. Now, if you look at what I told you, that the mass number of products on the right hand side should be balanced with the mass number of the left hand side. Now we want to see, were there neutrons produced or not? How many were they? You realize that the total mass number on the left is what? 235 plus 1 is 236. Good. Now it means also the mass number on the right hand side of the arrow should also be 236. But when we add 144 plus 89, we see we are having 233, meaning it is less by 3 from the mass number on the left hand side. So it means that 3, those are the number of neutrons which will be produced. That's why you see we have here the neutrons produced, which are 3 of them. And if we get the mass number 3 times 1, each neutron is having a mass number of 1, meaning the total mass number of the 3 neutrons will be 3, plus the one which was this side 233 will be 236, which balances with the mass number on the left hand side. And even when we look at the atomic number on the left hand side, we have 92 plus 0, which is 92. And when we look at the atomic number on the right hand side, 56 plus 36, that gives us also 92 plus 0, because 3 times 0 is 0, so still it is 0, so it will remain 92. So the equation will be balanced. Remember, we said in both reactions there is a lot of energy that will be produced when it happens. Here a lot of energy will be produced when the two combine. They will produce a lot of energy, heat energy. And here also, when this one breaks up, as it is breaking up when it is disturbed by the neutron, it will also produce a lot of energy. Now, this nuclear fusion here is very, very crucial when it comes to the sources of energy in the sun and the star. If you recall, when we were looking at your topic of stars and galaxies, you must have looked at how stars are formed. That at that stage where the star or where the protostar starts happening, you see that the dust particle or the gas, the dust of the gas dust or the gas particles come together, and as they keep fusing together, coming together, they produce a lot of heat, and that is how the star starts getting formed. Now, even in our sun, it has these hydrogen atoms or helium nuclei which keep fusing together. As they are fusing together, like let's say as one hydrogen is joining with another hydrogen to produce a helium, there is a lot of energy that is produced, and that energy is what for us here we receive as sunlight, as what we receive that heat coming from the sun. So next time the question comes to you asking you about, you explain where the sun gets its energy from, you should know that the sun gets its energy from nuclear fusion happening in its core, whereby hydrogen atoms are fusing to produce helium atoms, or helium atoms are fusing to produce lithium, and so on. So as the nuclei fuse, they produce that energy which gives sunlight and heat, which is very, very important for life here at Earth. If we didn't have the sun even just for 1 week, you would see things changing rapidly. People would fall sick, plants will die because no photosynthesis will be happening, human beings will start dying. It is very, very crucial, it is important, but it all starts just from the simple physics here, fusion. When we look at the advantages, we've seen how these two happens, meaning you already see, even if I stopped there and I ask you what are the advantages of a nuclear reaction in our daily life, you already know. It is a source of energy from our sun, and which sun enables everything to happen here on Earth, you see. So some of the advantages are, like if we look at the nuclear fission, you see under a nuclear fission or breaking up, Fi,